Let's compute the limit of x squared over sine 3x squared as x approaches 0. Observe that the limit of the numerator is 0 and the limit of the denominator is sine 0 or 0. The key is that the limit of the expression inside sine is 0. So we may use our preceding results. To produce the desired form, we need to pair the sine 3x squared in the denominator with the 3x squared in the numerator. So in this case, we just need to multiply and divide by 3. Thus, we have the following. The limit as x approaches 0 of 3x squared over sine 3x squared times 1/3, where this quotient is of the form f of x over sine f of x, where f of x approaches 0 as x approaches 0. So we have 1 times 1/3 or 1/3. Next, let's evaluate the limit as x approaches -1 of sine of x squared minus 1 over x plus 1. Now, as x approaches -1, the denominator approaches 0, and the numerator approaches sine of 0, which is again 0. Again, the expression inside the sine function approaches 0 as x approaches -1. Thus, we need to pair the sine x squared minus 1 in the numerator with an x squared minus 1 in the denominator. And since x plus 1 is already a factor of x squared minus 1, we just need to multiply and divide by x minus 1. Thus, we have the limit of sine of x squared minus 1 over x squared minus 1 times x minus 1, where again, this is of the form sine f of x over f of x, where f of x approaches 0, in this case as x approaches -1. So the limit of the limit of this quotient is 1, and the limit of the second factor is -1 minus 1 or -2. Therefore, we have 1 times -2 or -2. Next, consider the limit of sine 3x over sine 5x as x approaches 0. This is of type 0 over 0, and note that 3x and 5x both approach 0 as x approaches 0. Now, no matter how tempted you are, do not cancel sine, no? And then cancel x here, no? And say that the limit is 3/5. That that's wrong. Okay, so how do we remove the indeterminacy here? Well, we need to pair sine 3x in the numerator with the 3x in the denominator, and the sine 5x in the denominator with a 5x in the numerator. So we multiply and divide by 3x and also by 5x. And then we rearrange expressions. So in this case, we get the limit as x approaches 0 of sine 3x over 3x times 5x over sine 5x. And now what remains unused, we have 3x over 5x or 3/5. Okay, and by our generalized results, the limit of this is 1, the limit of this is also 1, so we get 1 times 1 times 3/5 or 3/5. Next, consider this limit. The limit of the numerator is tangent 0, which is equal to 0, while the limit of the denominator is 1 minus cosine squared 0, or 1 minus 1 squared, or also 0. So again, this is indeterminate of type 0 over 0. And note that the limits of 3x and 2x as x approaches 0 from the right are both equal to 0. Now, notice in this case that 1 minus cosine squared 2x is just equal to sine squared 2x. Now, to use our results, we will rewrite the tangent function in terms of sine and cosine. Also, to shorten our solution, we will separate the factors now as follows. We have the limit of sine 3x, which comes from tangent 3x, times sine of 2x, quantity squared, times 1 over cosine 3x, where this comes from tangent of 3x. Now we need a 3x in the denominator here, so we multiply also by 3x here. Since there are two copies of sine 2x here, then we need two copies as well of 2x in the numerator. So we divide by 2x quantity squared as well. Okay, and rewriting, we have the limit as x approaches 0 from the right of sine 3x over 3x times 2x over sine 2x quantity squared times 1 over cosine 3x times 3x over 4x squared, or 3 over 4x. Noting that cosine of 0 equals 0, we have that the limit has the form 1 times 1 squared times 1 over 1 times 3 over 4 times 0. So this, in effect, is of the form 3 over 0. And in this case, since x approaches 0 from the right, then this factor approaches 0 through positive values. Therefore, we say that the limit of this expression as x approaches 0 from the right is positive infinity. Now, consider the limit of 1 minus cosine x over x squared as x approaches 0. Now, if we factor out 1 minus cosine x all over x here, then the remaining factor is 1 over x. Now, 1 minus cosine x as x approaches 0 approaches 0, while 1 over x as x approaches 0 becomes infinite. So the indeterminacy remains. And in this case, it seems that our result for the limit of 1 minus cosine x all over x as x approaches 0 is not helpful. So how do we remove the indeterminacy here? Well, since the result for 1 minus cosine x all over x does not help, and this is an indeterminate limit of type 0 over 0, then perhaps we need to use the limit of sine x over x instead. So we need to rewrite this in terms of sine. And as before, in our proof of the limit of 1 minus cosine x over x being equal to 0, the trick is to multiply and divide by 1 plus cosine x. In order to get 1 minus cosine squared x in the numerator, which becomes sine squared x. All right. Note that we also factored out 1 over 1 plus cosine x because it does not contribute to the indeterminacy anyway, because its limit as x approaches 0 is 1 over 1 plus 1, or 1 half. Now, sine squared x over x squared may be rewritten as sine x over x quantity squared, and applying our limit theorem, the limit of this is 1 squared. And so we have 1 squared times 1 half, or 1 half. Now, the next example is a reminder to be careful with the use of our results. Just because you see sine x over x does not mean that the limit is 1. Note that the limit of the numerator is sine pi over 2, which is 1, and the limit of the denominator is pi over 2. So this is not indeterminate. And so we just evaluate and we get 1 over pi over 2, or 2 over pi. For this next item, we just evaluate the limit starting with the inner function. Now, as x approaches positive infinity, 1 over x approaches 0. And this is in the domain of the cosine function. And remember, the cosine function is continuous on its domain. So we have the limit of cosine 1 over x as x approaches positive infinity is just the cosine of 0, which is 1. Similarly, for the limit of tangent 1 minus cosine x all over x as x approaches 0, first note that the limit of the expression inside the tangent function is 0 by our limit theorem. Moreover, the tangent of 0 is defined. It is sine 0 over cosine 0, which is 0 over 1 or 0. So 0 is in the domain of the tangent function. Therefore, the limit above is just equal to tangent of 0 or 0. Now, consider the limit of cotangent x as x approaches pi from the right. Substituting, we have cosine pi over sine pi, but sine pi is 0, so pi is not in the domain of the cotangent function. However, we can note that by writing cotangent x as cosine x over sine x, then we have something of the form, or sorry, we have something whose numerator approaches cosine pi or negative 1, and whose denominator approaches 0. So the limit is infinite, and we just need to determine the type of value sine x passes through as x approaches pi from the right. Now, what does x approaching pi through values greater than pi mean? First, let me just complete this drawing of the unit circle. Okay, so x approaching pi from the right means x approaches pi through values greater than pi. So the angle approaches pi from the third quadrant. And in the third quadrant, the value of the sine function is negative. So sine x approaches 0 through negative values. We have negative 1 over 0 through negative values. So this limit is positive infinity. Alternatively, one may use the graph of the cotangent function if one has it committed to memory. So this is the graph of the cotangent function. Observe that it has a vertical asymptote at x equals pi. And based on the graph, the limit of cotangent x as x approaches pi from the right is indeed positive infinity. And that concludes this lecture. Try to work on the following exercises on the intermediate value theorem, squeeze theorem, and limits involving trigonometric functions. If you have any questions, please contact your teacher or teachers. Thank you for listening. Have a good day. Goodbye.